Just a minute. Let me turn off Wi-Fi. Okay, so yesterday, first, do you have questions about anything we talked yesterday? Okay, so even if you have questions about what we talked yesterday, you can just interrupt and ask questions. We will continue from the same place. Yesterday we talked about array gain and directivity factor. Okay, so array gain is actually the improvement in signal-to-noise ratio of using the array beamformer compared to a single sensor. So if we have sensor array, we have multiple sensors anywhere in space. Okay? So we can call any one of the sensors as number 1, and then we can count them, 3, and so on until we have m sensors. So usually we have here m inputs. We multiply each sensor signal with some weight. So here we have certain weights. Let's call it W. And then we have here the beamformer output. We will talk about more, but usually what we take the signal that is received in each one of them, 1, Y1T, and so on, Y2T, and so on, all of them. So the output, if we call it ZT, is actually can be written as a summation of taking the weights. If we talk about filters, so each one will be like HIT convolution with YIT. These can be the weights, the filters, from I equals to 1 to M. Or we can write it in the frequency domain as ZF, summation from I equals to 1 to M. We can call it WF, so it would be some weight, YIF. So this is like superposition of the signals that we measure by the sensor array. And then suppose that the signal-to-noise ratio is the same for all the sensors. So we can define as on one of the sensors input SNR. So it will be relevant to one of the sensors. Let's assume that the signal-to-noise ratio is the same for all the signals. And we can define the output signal-to-noise ratio here. So it will be output SNR. So the ratio between output SNR and input SNR, we call it array gain. So it will be output SNR divided by input SNR. So this ratio is actually the same as what is the gain that we achieve for the desired signal compared to the gain which is a result for the noise signals. Okay, so it's the same. It's the same. Because we have some gain for the desired and some gain for the undesired signal. Yes?
So here we assume the inter-element spacing to be less than lambda.
Actually here, I don't assume anything about the configuration of the array. It doesn't really matter. And after the output, suppose that I have certain weights or certain filters. I get output here. And because it's linear, this is a linear beamformer. Beamformer, it means that we have some weights or some filters. It's the same, the frequency domain. So here we get some output SNR. We can write the output as summation of two components. One is desired, one is undesired. Okay? And the desired, the power of the desired compared to the power of the desired in one of the sensors here, there is some ratio. This is the gain of the desired, like this. And if we have some interferences, some noise, we have also what is the noise here compared to the noise in a single sensor. This is the gain of the undesired, the gain of the noise here. So this ratio is actually the same as output SNR divided by input SNR. Okay? So we want this to be as high as possible. So we have more gain in SNR. But when we measure that, so this is called array gain. But the array gain depends on usually the direction, what is the gain for the desired, and also what is the gain for the undesired, which depends on the noise environment. So we said that if we define this for white noise, especially white noise, we call it white noise gain. So we call it white noise gain, which means what is the array gain when the noise is spatially white, which means that the noise is a thermal noise, which is independent in any field, any sensor. And another definition is directivity factor, which means what is the array gain when the noise is diffuse noise. It comes from all directions with the same power. So these are definitions. And generally, if we have this array gain, we obtain it. This is the directivity pattern. So the directivity pattern for a certain direction, this is the direction of the desired source. The magnitude squared of the directivity pattern in the desired source direction, it means this is the gain of the output desired signal compared to a single sensor. And if we have diffuse noise, it comes from all directions with the same power. So if we take the the integral on a sphere of the directivity pattern, the magnitude squared of the directivity pattern over all directions, what we get here, this is the gain for the diffuse noise. So we can define this as the directivity factor. Okay? Sometimes we want to maximize the directivity factor in some way. Okay, so how we change this formula, how we change this when we have a near-field source. So near-field source, it means that the desired signal is close to the array. But the noise still, it comes, if we want to compute the directivity factor, the noise comes from all directions with the same power. So what we need to change is the formula for the directivity pattern. How do we do that? So for far field, we have that the distance of the source is much larger than L squared divided by lambda. But if this is not satisfied, it means that the desired source is in the near field. Okay? And then for far field, we can assume that the source transmits plane waves. But we cannot approximate the source signals as plane waves if the source is in the near field. So we need to change the plane waves into spherical waves, like this. So we need to take into account two things. One, is the curvature of the wave, of the propagating wave, because it's in the near field. Another thing is the decay of the magnitude of the plane of the spherical wave by the distance. So it decays inversely proportional to the distance. So we need to take those two elements into account when we have the directivity pattern. Afterwards, everything will be the same. So it's important to see how we change things. So instead of taking, for example, if we have a linear array like this, and we have a plane wave that comes from here, so we can call this number 1, 2, and so on until we have m sensors. And suppose that the distance is d between two sensors. So it's a uniform linear array. Uniform linear array. So when we measured the distance or the delay of the propagating wave that comes from a certain direction, we could assume that the distance here is d, the distance of a sensor, n sensor, to the first sensor is d multiplied with n. And then we take into account the direction, okay, for the plane wave. But for a spherical wave, this is the distance between two sensors. See? So the distance between two sensors is like this. What does it mean? That we take, suppose that the source is somewhere here, and this is the reference sensor. So we call this D0 R phi, and we take this distance, we call it dn R phi. This is the n sensor. So the difference between the distances will be like this. Okay, so this minus for 0. And then we need to change this expression that we wrote for the directivity pattern. So this expression was obtained when the distances between sensors is nd, okay, so inter-element distance is d, and we have elements from minus n minus 1 divided by 2 to n minus 1 divided by 2. So we have n elements, and we assume that it's symmetric, but it doesn't have to be. It's just this expression is for symmetric array. So we need to change this nd cosinus phi, the distance, by this distance, because this is more general for spherical spherical waves. If we replace the spherical wave by plane wave, we get nd cosinus phi. Okay, so it will be the delay between the propagating wave that hits, impinges the first, the reference sensor and any other sensor, any sensor. Okay, but this is not enough, because we need to take into account also the decay of the acoustic wave. So the decay of the acoustic wave here, so we take that also into account, because it decays according to the distance. So without the weight, this is actually the acoustic wave that hits the sensor, the any sensor, compared to the reference sensor, which here we call it number 0. So this will be the directivity pattern for near field source. So any near field source, at the output, what do we measure? What do we measure? Directivity pattern, what does it say? That any, for the near field, that any source that is at a certain position, we can call it at a certain position, r, theta, phi. Or we can assume that theta is in a different place. But we can assume that we have a certain position of the near field source. For far field, we don't need to specify r, the distance, because it's far field. But for near field, we need to specify r in addition to theta and phi, the direction. This is the direction, this is the distance. Okay, so what does it mean, directivity pattern? It means that what is the strength of the signal at the output of the beamformer. So if we use certain weights, like here, certain weights, and we take the summation of the signal that impinges all the sensor array, like here. So we assume that we have like this. So this will be, let's assume that we have an odd number, and this is sensor number 0. Here we have 1, 2, and so on, 3, minus 1, minus 2, minus 3. So each one we multiply with W. And each one has a certain weight, or we call it small one, okay? So it will be W0F, and so on, okay? So each one, it will be multiplied with a certain weight. And so on, and then we take all these outputs into account. So we take their summation, and here we have the output. So we ask ourselves, suppose that the source is in a certain position in space, and we get the signals here. What will be the strength of the signal here at the output? So this is the directivity. And we can normalize it, of course. We can normalize. So if we divide it by a certain value, it doesn't really matter. So we can normalize. And this summation is the strength of the output signal for a near field. So now we want to see what is the difference between far field directivity pattern and near field directivity pattern. So this is just an example. So we saw that for uniform linear array, the far field directivity pattern, it goes like, you see, it has some zeros, okay? It's a Dirichlet function, okay? So it has some, it means that for some directions, we have nulls. So with far field source that comes from a certain direction, from this direction or this direction, we will not get any signal at the output, because all the signals that come to all the sensors, and by the way, in this case, we have specific values, okay? So this is the far field, the blue line, and it comes from a certain, the direction is here. We assume that theta is pi divided by 2, 90 degrees. And for a certain frequency, 1 kilohertz, we have 11 sensors, and the distance between sensors is 0.1. Okay? So if we take the weights constant, 1 over the number of sensors, it's constant, we will get this directivity pattern. So we see it's maximum for the signal that comes from 90 degrees, from the broadside. Of course, because if the weights are all constant, let's say it's 1 over n, and the source comes from far field, from the broadside, and we accumulate all the signals that hits all the sensors, we will get a summation that it's maximum. That's why the maximum is 490 degrees. And of course, we can normalize it to 1, okay? And for certain directions, the summation can be cancel each other because they have different delay. And then we have cancellation of the signals, and then for certain directions, it may be 0. And for some directions, it's much smaller than the 90 degrees. But for the near field, suppose that we put the source is 1 meter away from the array on a circular, because we take 90 degrees. We just want to see the variation versus phi, the horizontal direction. So you see that the near field directivity pattern goes like this. And of course, we can also normalize it to 1. It doesn't really matter, because what we care about is the differences between different directions. So we see that for this near field source, it doesn't go to 0. So for any direction, because you cannot cancel exactly. Why do you think we cannot cancel exactly in this case? So we have 11 sensors. What do you think? What made this situation that you cannot cancel the source that comes from any direction? The summation of the signals with constant weight, they cannot cancel each other. What do you think? Because we have two differences between near field source and far field source. What are the differences? Yes, it's spherical. So the differences is in the phase. Okay? So in the phase. So it doesn't go like something like horizontal. So the differences in phase between two sensors are different than far field. But also the decay, the magnitude. So these two factors, especially the decay, because the decay depends on the distance, make this near field directivity beam pattern such a way that it doesn't cancel. Okay, so now I want to ask you a question. Is it possible to have a null here by changing the weights? The weights, this is the result of the directivity pattern when the weights are all constant. All the weights are simply 1 over n. Okay? WIF equals to y over n. So the question is, can I change the weights? The weights are complex in the frequency domain. Can I change the weight such that I will get for a certain direction null? Is it possible? Yeah, it's possible. Is it possible to change it that I will have 2 nulls? 2 nulls for 2 different directions. Is it possible for 3 nulls? And so on. How many nulls can I get? Is it possible to design it in such a way? So these are questions that we will ask. So when I say that we want to change the weights to get a beam pattern, near field directivity pattern and beam pattern is the same. Okay? So if I want to get a different directivity pattern, desired directivity pattern, by changing the weight. This is called beamforming. Okay? And we will see how to design beamformers. But not only that. So when I design beamformers, I can ask myself, maybe I can change also the location of the sensors. So I can change the number of sensors. I can change their location. It doesn't have to be on a line. I can change it to be anywhere. How do I design sensor array? Where to put? How many sensors? Where to put them? And so on. And then I need to design the weight such that I will get a desired either far field beam pattern or near field beam pattern. It depends if the source is in the near field or far field. Okay, and another thing that I want to emphasize, that when we took this equation, okay, so the near field, you see that if I go back to this equation, you see, so this is the directivity factor that was obtained for far field. So if you want to change it to near field, you just need to change here. Here you take the directivity pattern of the far field. And the question is why? So if this is the array gain for far field, what we saw before. And now we saw that we need to change the directivity pattern is different for near field. So if we want to compute the near field array gain, what does it mean array gain for near field? Only in the numerator. Okay? Because you understand why. Because the desired source is in the near field, but the noise that comes from all the other directions is the same as the far field. So here we don't change it, which is important. Important to understand this. Okay? Any? The array gain depends on what? It depends on the, no, of course, yes. This is the array gain. What we saw, this expression, is for the far field sources. So that's why here it doesn't depend on R. But I agree with you that for if we compute the array gain, or here, directivity factor, so if we compute the directivity factor for near field source, it will depend also on R, the distance of the source from the array. But we need to change the directivity like we used for the near field only here in the numerator. In the denominator, it will be the same expression. Okay? So we change here in the numerator, we need to use this expression. You see? This expression. And actually, I agree that here it needs to be also a function of R. So it's missing here. But it needs to be as a function as R, because you see it depends on R. I will add it. Anyway, this expression you use only in the numerator of the directivity factor, not in the denominator. In the denominator, you put here the far field. So it will cancel here, and here you will get nd cosinus phi. Okay? Any other questions? Yes. Okay, white noise gain. So if we take the white noise gain, what does it mean? So it's a good question. Actually, we will talk about it. You see, so how do we change the array gain for white noise? So we don't use this denominator. It will be different because Actually, we don't take noise that comes from all other directions. So we will see how to modify this. Denominator is the same, okay, because this is the gain for the desired source. So either near field or far field. We change only near field or far field in the numerator. In the denominator, if it's diffused, it looks like that. If it's not diffused, you need to change that because it depends on the noise. We will see. Okay, we will talk about it. Any other questions? Okay, let's move on. So we understand how to change things, how to modify for near field. Okay, so let's talk about beamforming techniques. Beamforming, it means that we want to design these weights according to some specifications or desired features. How do we do that? So we will talk about classical beamformer, maximum directivity beamformers, because sometimes we want to design these values such that the directivity factor will be maximum. And this part I will skip. The generalized side lobe cancer is an adaptive beamformer. We will talk about when we reach adaptive beamforming. So I will skip that for this overview. Okay? So in order to talk about beamforming, how to design these weights, we need to talk about noise fields. So we already talked about noise field. We talked about spatially white noise. We talked about diffuse noise. And also we have sometimes directional noise. If a noise source comes from a certain direction, it's called directional noise. And of course, in practical environments, it's combination. It's more complicated because we have some surfaces, the noise hits some surfaces and propagates with a certain transfer function and so on. But the simplest or the standard simplest noise fields are three types. Okay? First, we have coherent noise. Coherent noise, so we define it according to the coherence of the noise that is received in two sensors. Suppose that we have any two sensors, sensor I and sensor J. So here we have the cross-spectral density between the signals, between the noise signals in the two sensors. And we normalize it by the square root of the autospectral density of the noise that it received in sensor I. And this is the spectral density of the noise that is received in sensor J. So we can, this is definition of coherence of signals between two sensors. So if we measure the magnitude squared coherence, we take this value and we take the magnitude squared. So it's always between 0 and 1. So for coherent noise fields, it means that the magnitude squared coherence between any two sensors is very close to 1. So this is obtained when we have a noise source or interference without any reflections. So if we have a noise source and we don't have any reflections in the environment, it hits or it is measured by each sensor by simple delay. Okay? So we see that if we have a simple delay of signals between every two sensors, so if you take a sensor and another sensor, and the relations between the signals in the two sensors is simple delay, we have magnitude squared coherence which equals to 1. Okay? So in free field or when the walls are very far, so reflections can be neglected and so on, or in anechoic chamber, for example, for acoustic waves, or in the air, if you have electromagnetic waves and it hits without, you can neglect reflections, you will have magnitude squared coherence, which equals to 1. And this is a coherent source. Incoherent noise field, it means that the magnitude squared coherence is close to 0 or even 0. And this is true for thermal noise. So if you have in each sensor different type, different noise, maybe even it's same level, but it's statistically independent or incoherent, the coherence between them is 0 because it's thermal noise, it's independent, then the magnitude squared coherence will be 0. So this is called incoherent noise field. And we can also call it spatially white, okay? Because in each 2 points that you measure the noise, it's independent. Okay? So it's spatially white or incoherent, same. Another noise type we talked, diffuse noise field. So diffuse noise field, we assume that the noise comes from all directions with the same power. So what is the coherence between two sensors? So if we have noise that comes from all directions with the same power, if you measure the coherence between the signal, the noise signals in two sensors, any two sensors, actually it depends on the distance between the sensors and the frequency of the signal. So in low frequencies, we have higher or lower coherence. What do you think? Low frequency compared to high frequency. The coherence will be lower or higher for diffuse noise? What? Think about low frequency. So for low frequency, the dependence or the correlation between signals will be higher or lower compared to high frequency? Higher, okay? So for low frequency, the coherence for diffuse noise between two sensors will be higher. So this is something that can be derived, actually. So this formula can be derived that the coherence between two sensors goes like a sinc function that depends on the frequency and the distance between the sensors. And also the speed of the propagating wave, the speed in the environment. But it goes like this. So you see that it's F divided by C is actually 1 over lambda, the wavelength. So if we take the distance divided by lambda, so the distance between two sensors divided by the wavelength, so it goes like a sinc function of that. So you see that if the distance increases, the correlation decreases very quickly. The distance compared to lambda, because it's relative to lambda. And if the frequency is low, is very low, which means that the wavelength is much larger than the distance, of course we have high coherence. Okay, so the simplest way to do beamforming is actually steering. Okay, steering. What does it mean, steering? It means, okay, so let's talk about far field sources, far field beam pattern. Okay, so we saw that for far field sources and with uniform linear array, if we take weights which are constant, 1 over n, the beam pattern or directivity pattern as a function of phi. Okay? It looks like this. Something like this. Okay, so if we plot it with polar plot, so it goes like this. Okay, something like this. So here, for maybe 90 degrees, we have the maximum. Why? Because if we have an array and the source comes from the far field from this direction, from 90 degrees, this is phi. Okay, this is x. And this is the direction of the source. So if it comes from 90 degrees, we have maximum gain. So we have the maximum gain in that direction, which means that the output signal, the gain, will be maximal for 90 degrees, for broadside direction. If it comes from another direction, it depends according to this. Suppose that we want to have maximum gain for different directions. Instead of 90 degrees, we want maximum gain for a certain direction, phi 0. Maybe 40 degrees, 60 degrees, a certain direction. What can we do? So you see the signal that comes for each that is measured in each sensor comes with a certain delay. First it hits this one, next this one, next this one, and so on. And we know exactly the delay. How do we know? Because we know the configuration of the array. For here it's a uniform linear array, but for any array, if we know the position of each sensor in space, we know exactly what will be the delay that for the propagating wave that hits different sensors. So if we compensate for this delay, what do we get? If we compensate. So instead of here, so this beam pattern, how did we obtain this? What did we do in the time domain or in the frequency domain? It's the same. So here we took the output of the beamformer as 1 over n summation from I equals to, it doesn't really matter if we take how we count it. We can count it from 1 to n. Okay? And suppose that the signal hits here with xt. So we obtain this one because we didn't do anything. It's just xt. If it comes from 90, you can say that it's a function of t, and the source comes from 90 degrees, so we will get maximum for 90 degrees. But if we take something like this instead of this, we take it as 1 over n summation x minus xt minus tau I, so certain delays, which depends on the sensor. And suppose that we choose these delays exactly such that it compensates the delay for a certain direction phi 0. So what will happen? This will move. So instead of 90 degrees, it will move to phi 0. The maximum will be phi 0. Okay, so if I take this, it will move to this. And this will be phi 0. So we can do it in the time domain. Like this. Just a minute. here. So we can do it in the time domain like this, where we choose tau, these delays, to be specific according to the delay, or we can do it in the frequency domain like this. So instead of delay like this, so we have modulation, which compensates the delays for the signal, for the propagating wave that comes from a certain direction, phi prime. So this kind of beamforming, you see, we didn't change the magnitude of the weight. The magnitude of the weight is still 1 over n. We just change the phase. The phase. So this is called delay and sum, because we delay each sensor signal, and then we take the summation. So you can ask, okay, why do we change only the time for the delay? Maybe we change also the magnitude of these weights, and then we call it filter sum. So it's filter and sum. So in general, filter sum beamformer, we can choose any weights like here, which includes magnitude and phase. And we can achieve a desired directivity pattern. Not whatever we want, but maybe there is a desired directivity pattern, and we can reach to some degrees. We can approximate or come close to this desired beam pattern. Can we achieve any beam pattern? Okay, so suppose that we put the sensors, we have a certain number of sensors, n sensors, and we put them in space, in a certain position. Can we achieve any beam pattern? Can we achieve any shape of the beam pattern? No, of course not. Okay? But we can come closer by certain, maybe we can come closer as much as possible, because we limit the number of sensors, and we limit the position. But if I ask you, can I achieve any beam pattern with any number of sensors and without any limitation, put them wherever you want? Okay, so of course you can come very close to whatever you want. This is like an ideal case, but in practice you have limitation. You have some limitation on the configuration of the array. You limit the number of sensors because you don't want to use too many sensors. Each sensor, you need a sampler and so on, hardware to sample the signals that are received, and also the sensors and the sampling. The sensors, you want to put them in a certain place. Maybe you don't want too large sensor array. You limit the space, you limit the number, you limit where you put them, and so on. You have some limitations. Suppose that you want to put a sensor array on glasses, smart glasses. You cannot put it like this, sensor array like this, okay? You have limitation where to put. And also you want to limit the number of sensors because it requires more power. The battery is also a problem, okay? So under these constraints, another question. Suppose that I don't tell you what is the desired beam pattern. I just tell you which direction will be the maximum. Can I design these weights? Can I design these weights such that the maximum will be for a certain direction? Yes. Okay. Now, suppose that not only that I want the maximum to be in a certain direction, but I want the directivity factor. What is the directivity factor? The maximum here divided by the integral for all the directions. I want to maximize it. So I want to design these weights such that the directivity factor, the ratio between the maximum and the integral, will be maximum. Is it possible to do that? Yes. call this kind of beamformer maximum directivity beamformer. Okay? So we will learn about it. This is very common way because you see maximum directivity beamformers are very important. Why? Because sometimes you don't know, suppose that I design the weights in advance. It's not adaptive. I would like to design the beamformer in advance without knowing what is the noise environment. Suppose that I put a beamformer, I design a beamformer, fixed beamformer, and the smart glasses. And I don't know if this noise comes from this direction, from another direction, or maybe it comes from all directions. So the simplest way to design a fixed beamformer is to design a beamformer that maximizes the directivity. Because I don't know in advance what will be the noise, so I assume that it can come from any direction. So it makes sense to design these weights, the beamformer, such that it will maximize the directivity, the ratio. So if it maximizes this ratio, it means that the side lobes will be as low as possible, which means that all noise that comes from all directions that outside the main beam will be, the gain for them will be as low as possible, which makes sense. Okay, so this is how it looks. Okay, another issue, so we will talk about maximum directivity beamformer. Another issue is, you know that when the frequency increases, we saw that the problem here, if we talk about the beam pattern, the beam pattern looks like this. So the width, this is the width of the main beam. So when the frequency increases, the width of the main beam decreases. Why is it a problem? Can you tell me? Why is it a problem? Why do we care? Okay, so it's narrow. Is it good that it's narrow? Or is it bad? Two things, okay. Okay, if it becomes narrow, what is the problem? Okay, so actually we have two problems if it's narrow, okay? Two problems. First, suppose that I put array on smart glasses. So the desired source needs to come in front of me. So if it's too narrow, I need to look exactly to the person. If I move a little bit my head, that's it. I cannot hear it, maybe, because it will be like side lobe. So I don't want something that is too narrow. I want something which is wide enough. So I don't need to look exactly to that direction. Also for adaptive beamforming, even if I do steering, suppose that I do steering to a certain direction, because I know that the source comes from a certain direction. So I can do steering, digital steering. Okay, digital steering, it means that it's according to the weight. I don't need to move the array to the side. So maybe this direction that I estimated, maybe it's inaccurate. Maybe I don't know exactly the direction. Maybe it's here, it's not here. But I steer it to a different direction. But it's too narrow. So if the width is too narrow compared to the error in the direction of arrival estimation, yes, then it's not good, because I will miss the direction. I will miss the desired source. Okay. Now suppose that when you go to high frequency, it's more narrow. So for low frequency, it's wide. Which means that when I measure, when I get the output signal at the output of the beamformer, So for low frequencies, the main beam is wide, so I will get the desired signal for low frequencies. But for high frequencies, when the beam is narrow, I will not get it at the output. The gain will be low because it will be, maybe it will be outside of the beam because the beam is narrow for high frequencies. So the effect of the beamformer will be like low-pass filter. Low-pass filter distorts the desired signal. So we don't want these two problems. So what we want actually is to design a sufficiently wide beam, but not too wide. Why? Because if it's too wide, also it's not good, because I will obtain more noise at the output of the beamformer from the main beam. But so I don't want too wide. I want it to restrict the width. And I also want that the width will not depend too much on the frequency. So when I increase the frequency, it will not be narrow. It will remain the same width for all frequencies. And the question is how to do that. Okay? So we will take 10 minutes break to think about how to do that. We will continue from here. One of the solutions is subarray beamforming. But this is a simple solution. There are even more sophisticated solutions, but we will talk about this.